everybody. Just give me a couple clicks away from getting our video ready for us. Okay, so we're looking at Unit 3, Chapters 8 and 9, where we've been talking about systems of equations. And in this video, I want to look at 9.2, which is quadratic inequalities in one variable. These are a couple of key words there. We're going to be looking at quadratics instead of linears. But also, we're only going to be looking for one variable. We're not looking for both x and y. We're just looking for the x values. So let's see what this involves. The objective is that you will be able to model, solve, and interpret problems that involve quadratic inequalities. A couple words are going to come up as we go through it, so be watching for test points again, and also open and closed points so that you can understand what we mean by open and closed points. So what I'd like to do actually is just throw a question at you and see if you can just use your common sense to find the answer. Let's see if you can use your intuition. So if I said to you, okay, I'd like you to solve this. In other words, I want you to figure out what x would be equal to, such that it would make this thing either equal to 0 or smaller than 0, so a negative. What values of x will do that for us? So keep in mind that all you're looking for are the x's in this, and I'd like you to pause the video and just give it a try first. How might you try to do it? So, and we're going to take a look at your solutions, but we're also going to take a look at how you did it, because there are a couple of ways, and it's possible that you may choose one of the ways that I am going to show you and think, okay, that way is nice and clear and easy to me. You may decide. The first one I want to take a look at is, what if we had a graphing calculator and just decided to graph this thing? What if I graphed this quadratic and looked for what values of x would make it either equal to 0 or smaller than 0? So if I graphed it on Desmos, here it is. Well, I know it's equal to 0 when it's a negative 1 and a 3. And then I know that the values will be negatives when they're down here. So it's all these x's along in through here that will make my quadratic either equal to a 0 or smaller than a 0. So I'm looking for all those values of x for which the graph of this thing lies on or below the x-axis. And sure enough, as we've said already, our answers lie between negative 1 and 3. And the way to write that using set notation is x, curly brackets, of course, x such that x is greater than or equal to negative 1 and is less than or equal to 3. So that's one method. You use your graphing calculator, take a look at it, try to decide for yourself where the function is larger or smaller than 0, and go from there. But as you know, it's not always possible to use a graphing calculator, so we do have some other simple methods we can do. One method that some people like is where they use a number line. Just a simple number line, though. And they take this guy and think, okay, well, where are the strategic points? Well, I know that one of the strategic places would be where it's actually equal to 0. So I'm going to stop and figure out where that is. And so we stop and figure out where it's equal to 0 by factoring our equation. And so we look for what multiplies to be negative 3 and adds to be negative 2. So we find these two numbers. And we realize, okay, on a number line, this is where this thing will be equal to 0. So now my answers can either be smaller than this guy, in between these two, or up above. And I want to know which ones. So I could very easily just take some test points, choose a random number down here in the negatives, one in here and one there, and test them. And that's what you see that they've done. They chose a negative 2, and they realized that their answer didn't make sense, because when you put it in and got a 5, 5 is not less than or equal to 0. They put in a 0, because that's one of your easy ones in between, and they realized their answer was negative 3. So yep, that one worked. And then they took a test number that was above here. They took a 5, they plugged it in, found it was 12, made no sense. So you could see based on these test runs that you did that your answer solution is right in here, which we found in the first one as well. And we would write it in the same way with set notation. Now there's one more way you can do it. And I actually prefer this because I find the math faster and simpler. And what it is you break the quadratic down into its factored form. So, oops, I guess I'm missing it there. Sorry, the factored form is not here, but the factored form would be x plus 1 times x minus 3. less than or equal to 0. So what I'm going to do is test each one of those. So if I test, first of all, x plus 1, and I put a line where x is equal to 1 and x is equal to 3, and I'm going to test what happens in these intervals in between, what I want you to realize is you don't have to stop to figure out what the actual numbers are. You're just testing. So if I chose numbers that are like bigger, like -3 or -4, I would realize, okay, my answer is going to be a negative here. If I chose a number in between -1 and 3, like a 0, my number is going to be positive in here. And if I choose a number bigger than 3, it's going to be positive. So I have this combination of signs, if you will. Now let's add the next one. And so if we do it, sorry, there they come finally. All right. And then if we put the x minus 3 and do the same thing. So if I choose a number that is smaller than -1 and plunk it in there, I'm going to end up with a negative answer. If I choose a number in the middle, I'm going like a 0, I'm going to get a negative answer. And if I choose a number larger, I'm going to get a positive. So I've kind of broken it down, and then I'm going to take a look at, okay, well, what happens when I take those two and multiply them together? Well, a negative times a negative is a positive, positive and a negative, negative, and a positive, positive is positive. And so the one I'm curious about is the one where everything turns out to be negative. So in between -1 and 3, I have my solution. Okay, so let's take a few more times to try them, and we'll give you a chance to try the different methods and see what you think you like. Now, I'm going to actually leave out the graphing method because it does depend on a graphing calculator. And as you know, it's always good for you to be able to do these by hand. Okay, so the first one would be, all right, well, where are the strategic places? Well, I still want to know where it's equal to 0, even though I'm not going to use those points. They kind of are places where it's important on the number line. So I'm going to factor it, and I figure out that my numbers are -3 and 4. So I create a number line. You'll notice I'm using open points, which indicate that it's not actually equal to those. But what I have is a spot less than this, in between this, and greater than this. And I'm going to use some test numbers now. Choose some numbers. So choose a -5 and plunk it in, and you get a number, which actually works. Put in a 0 for the middle one. Nope, it doesn't work. And put in a 5 for the next one, and yeah, it works. So then we can see, okay, my solutions are here and here. And I write this in this manner, x such that x is less than -3 or x is greater than 4. Please notice we have not used the word and. If you use the word and, that would mean that both of them would have to be true in order for you to have an actual answer. And that would be impossible, right? We can't have something that's here and here at the same time. So we're stuck with just two individual ones. So we use the word or. And there's a picture of it. Notice I'm using the open circles to indicate the beginning of those intervals. Okay, now what if we did it in the other way where we tested things to see? We factored it first. So we factor it down into this. Let's see what happens. So if I used a -1 times the first factor and tested it out, well, numbers over here are going to be negative, and a negative and a negative would turn this guy into a positive. Numbers in here, let's like a 0, that would be a negative times a positive, so it's going to be a negative. Numbers in here that are bigger than 4 will definitely be positives for this part, and a negative and a positive means it's negative. And then I try this guy, and I realize, okay, numbers over here will be negative, in the middle will be negative, and here greater than 4 will be positive. So let's put it all together by multiplying all these guys together. This one times this one is negative, this one is positive, this one is negative. So when I look at, okay, what do I actually want? I want to know where it's negative. So I use this one and I use this interval. Okay. All right. So now let's try this one. Now we've got a bit of a more complicated quadratic now. We should turn it around so we can see what it is when it's equal to 0. You can stop and double check, but if you do, you're going to see that we can't factor this guy. We're going to have to use our quadratic formula. So in this case, I've plopped my numbers in, I find my two answers, and I get two decimals that I have rounded to one decimal place. So then I plop that on a number line using the open dots because I'm not worried about when it's equal to, just when it's greater than. I've got the different intervals, and now I use some test points. Choose some easy numbers, plunk them into your original, find your numbers, and what you're looking for is where they are greater than 12. So if you put them in where they're greater than 12, yes, no, yes. So I have a solution here, and a solution here. So when I write it, I've got to write or, right? And you can see that in your diagram as well. All right. Now, part of the reason that I just didn't bother to do that one, I mean, you could still use it, but the problem with using the factored version is it's not a very pretty factor. And so it's almost more cumbersome than you want. So the test points really work quite easily and well. Okay, so what does this look like if we try to do it in a real life problem? So a baseball is thrown at an initial speed of 15 from a height of 2. The inequality greater than 0 models the time t in seconds in the baseball in flight. During what time interval is the baseball in flight? Something like this one, we're probably going to be using a calculator. If we graph it, we get something like this. And notice we do know that our y-intercept is here. We do know that our x-intercepts are negative 0.13 and 3.2. But during what time is the baseball in flight would be indicated by this upper positive region of our graph. And so it's between 0 and 3.2. And so rather than using those x-intercepts as we did in previous purely algebraic questions, we use simply 0 is less than or equal to t is less than or, and there's no equal, sorry, less than 3.2. Okay. Now, just a couple points. If you need a graphing calculator to use from home there and you have an iPhone, please remember there are two apps that are really good ones and they're both free. This one is the Graphing Calculator X84, gives you a good graphing calculator, the TI-84. And this one, Calculate 84, also gives you a wonderful vision of the graphing calculator that you can use on your phone. So there you have it, modeling, solving, and interpreting problems involving quadratic inequalities. So your homework, here it is. It's also included on the Google Classroom page. So make sure you take some time to go through it really carefully. I have given you quite a number of questions in here, but only A and B only. If you find that you do A and you do B and you get them both wrong, you need to do more than A and B to kind of get into the groove and do them correctly. So use your discretion, make sure you're doing enough so that you are being successful as you go through these. And remember, if you have any problems, that you're going to put it in the Google Sheet for this particular lesson, and that would be 9.2 homework check-in. And then we'll take a look at it in a video later. All right, good luck, everybody.